Dr. Do It, and welcome to... And the bowl Hello, I'm Dr. Do It. Thanks for tuning in to Do It Again, an engineering and science demonstration show. I'm here at the National Aeronautics and Space Administration, better known to you as NASA. Welcome to my aerospace workshop, where students and I will be testing in this small-scale wind tunnel. So let's do it. Hi, Maria. Hi, Amar. Are we ready to begin testing?
We sure are, Dr. Do It.
We'll be recording data about how air flows over the model wing we've designed. We're hoping this cool new design will allow the plane to fly more efficiently.
But we'll have to test the wind tunnel first.
It's very important to test models and analyze the data. But Maria, how did you decide on that design? Where did this all begin?
Well, Dr. Do It, it all started while I was observing the many different wing designs on model planes. I began wondering and asking questions about those different designs.
So through your observations, you started to form questions.
Exactly.
Hey, Neutron. He's our cyber buddy who knows a lot about engineering and science. Neutron helps us understand new things. Ask a question or identify a problem. Define what you want to know. That's an important practice for both scientists and engineers. Thank you, Neutron. Scientists ask questions to help us understand the world in which we live. Engineers define problems and then test materials and design solutions to those problems. Now that we have a question about the different wing design, what is next? Hey, Jordan.
Hi,
What's
Dr.
happening?
Do It. When I got to school this morning, I forgot to bring my book. I left it here while I was doing research on the new wing design.
Well, did your research help Maria and Amar with their question?
Yes, it did. They were wondering how changing the wing shape would affect the airflow around the wing, so we researched. With more information, they came up with an educated guess about which design might work best and developed a model to test that guess. Bye, Dr. Do It. I'm off to turn my book.
Bye, Jordan. You know, research is very important in the engineering and scientific process. Hey, Neutron, what have you got for us today? Conduct research. Gather and evaluate information about a problem or question. Develop models and carry out investigations. So once engineers and scientists ask a question, they try to find out all that is known about the problem and then come up with an explanation from what they might think is the answer or solution to the problem. What's next, Neutron? Form a hypothesis, a possible explanation that you can test. I agree, Neutron. Okay, Neutron, I'll see you later. You need to use the information from your research to help you make a testable, educated guess. So, based on your research, can you predict what would happen if you changed the wing shape on your model?
If we change the shape of the wing...
Oh, it would affect how the plane flies.
That sounds like a good beginning for a testable hypothesis. If we change the wing shape on your model, we can prove whether the hypothesis is correct or not. Simply put, if you change the wing shape, then the flight pattern should change.
So, if we change or manipulate something on purpose, it allows us to test whether the hypothesis is true or not?
Yes, now you've got it, Maria. But it's very important to change only one thing at a time, so you can tell exactly what is causing the results that you are seeing. Well, hi, Neutron. Design an experiment. Test your hypothesis. To answer your question, conduct an investigation. And now, teachers, it's time for you and your students to participate. You have the wing model experiment ready. So state your hypothesis, identify the variables, and let's do it. Right, Neutron?
activity, you will experience the world of aerospace engineering as you work through a simple flight testing experiment. You'll need to perform repeated trials, collect and analyze data, and modify your designs for optimal results. Working through this process will allow you to experience for yourselves how scientists and engineers do their work. Begin by reviewing some technical terms along with the formulas you'll be using for calculation. Once you've gathered all necessary materials, you're ready to start construction of the models you'll be testing and the launch platform used to perform the tests. As you do your testing, double-check all calculations to eliminate the possibility of error, and be careful to control variables for accuracy. Pay special attention to the single variable that you, the scientist, are manipulating or changing, and the effect that variable has on the results you see.
3, 2, 1.
Most important, have fun, and let your creative thoughts guide your work. Who knows, you may someday be leading the next big technology breakthrough as you work on an engineering team doing aeronautical research for NASA.
The testing we conducted today reminds me of the flight tests the Wright brothers did over 100 years ago. Wouldn't it be great if we could go back in time and see them at work? Hey, Neutron, can you take us back to 1901 so we can watch the Wright brothers at work? Thanks, Neutron.
Something's not right. Something's not right.
I finished the graph on that data.
Well, I'm glad you did. I'm trying to make some sense out of this, and just looking at these tables of numbers, I'm not seeing it.
We've really got to talk about it. Well, before we get there, we know we had a problem, okay? We only got a third the lift this summer that we thought we'd get in our aircraft. I mean, we looked at the data from the experts. I mean, they said that we should have gotten this much lift. We made our wing bigger.
Yep.
Went
We
from
made our
165
prediction.
square feet to 208 square feet.
And not a single flight lined up with our predictions.
No.
Everyone was small. Everyone was short.
And we wrote down the angle of the hill. Every morning we went and measured the angle of the hill. We measured the speed of the aircraft.
Time aloft.
Time and loft, distance of the glide.
Across the ground.
Because we thought that would be important, you know, to know that for every flight.
And I trust those. I think that's good data.
Okay.
But when we make our comparison with the predictions, every case, well, your graph shows it really nice. Yeah, yeah. This is what we should have been flying, and this number down here is what we're actually getting.
About a third the lift.
Yeah. So something's wrong. Something serious.
We're going to have to figure that out.
Yeah.
Because either we've got bad information there.
Yeah, like I said, I trust the data we took. We were pretty meticulous.
Well, it's consistent, that's for sure.
Yep.
But if it's consistently wrong, then we've got to figure out, you know, if that's the case.
But this looks like in every case we are not getting as much lift as Lilienthal says we should be getting.
Yeah.
I don't trust Lilienthal. I mean,
yeah, but I'm glad we took all these numbers because we can, like you said, we can say we were consistent. We can see that things do agree in the numbers that we took.
Yeah. Now, what could be wrong? What could be wrong? There aren't that many variables here.
Well, we're going to have to consider that. Think about it for a little bit and see what you come up with. I'll think about it, see what I come up with, and then we'll kind of put that
Well, thanks
together.
for getting the graphs. The graphs, that's a much better way of looking at data than these tables. I know it was a lot of work to do that.
But you can see what it looks like.
Yeah, yeah.
Over, come look at this. Did you get an idea of what's wrong with the data?
Well, I think when we're trying to unravel this, we've got to get back to the mathematics.
Okay,
We've got to get back to the theory. The theory, I think, is correct. And the lift, which is our problem, is only a function of a few variables.
Right.
There's a pressure coefficient.
Okay, that's right.
That's a Smeaton coefficient. There's the area of the wing.
Right.
And we know what that is. There's the speed, and I think we've got that accurate.
Right.
And then there's this lift coefficient, which Lilienthal found on his swing arm device. There might be errors in there. I don't know.
So with that in mind, okay, with knowing that those are the variables, let's talk about each one of them and see if we can get an idea of how they affect it. Like you said, we know lift. That was, we measured how much
the answer.
lift, and
That's
we only
right.
got a third what we thought we'd get. We know area because
we can measure that.
The same
That's
every
easy.
time. Velocity we measured.
I think
we
we've got
knew
that accurate.
Distance, and we knew time.
Right?
And so distance divided by time, that's velocity.
Now, we did not determine that pressure coefficient. There could be an error there.
Oh, yeah, there could be, but they've been using that for years.
Well, that doesn't mean it's necessarily right. I mean, could be off. And it ends up in every equation. It ends up in the lift. It ends up in the drag. It ends up in the angle of attack that you fly at.
Okay, so if that's...
So it could be wrong.
Well, let's do this then. Let's do this. To see if it's wrong, let's take the numbers that we know that are right.
Okay.
Because we have those. And let's rearrange this equation, just a little basic algebra, and let's solve for that lift coefficient.
Good idea. Good idea. Yeah.
Okay.
All right, let's run some numbers. Let's see what we get.
We did the calculations, and the calculations did show that that Smeaton coefficient is not correct.
That's right.
We're going to have to verify that. We're going to need something to back this up with the experts if we're going to make that claim.
Okay.
And I'm thinking...
So, what's your thought?
Well, we have two ways to go. One, we can build another aircraft.
No.
Go back next summer.
I'm not sewing anymore. I've had it with the... No.
And that's expensive and time-consuming. So the other thing I like is kind of what you thought about and we discussed is doing some models.
Okay.
And rather than making big wings or big aircraft, let's make some, we've made some metal models.
Oh, you've made
here.
some small models.
And what we're going to do with these is we're going to put them in the wind tunnel.
Okay.
Great. And I think if we set them in there and set them all at the same angle, so that's not a variable.
All right.
And look at how each of these wings or these wing models can perform, we might get an idea of how best to make wings or how best to work
And what
things.
we'll learn on the models will apply to the big aircraft, and you don't have to build a big aircraft.
Safer, cheaper.
This is clever. Yeah. Now, what have we got here? We've got different...
These three are all the same area.
Okay.
So they have different, if you multiply the length times the width, it's all the same answer. Okay.
So if area was the only variable, these should all give the same answer.
Exactly.
Instead, because these are long and thin and that guy's kind of short and fat, we'll identify that one single variable, the aspect ratio of the wing.
And it's real important that, you know, when you're in the tunnel, that you stand in the same place all the time so we don't disturb the air.
Yeah, we've noticed that.
So the only thing that changes is the size of the wing.
Okay.
We can do some other tests, too, I thought about. Maybe we could test using wings in tandem.
Hey. Well, we've got two. What do you...
You know, NASA does a lot of testing in wind tunnels. Let's talk to someone from NASA.
A lot of research has been done in wind tunnels since the days of the Wright brothers. Hi, I'm Frank Quinto, facility manager of the 14 by 22 foot subsonic tunnel. In this wind tunnel, we test airplanes, rockets, and helicopters. You expect that in a wind tunnel. But did you know wind tunnels can test cars, parachutes, even sports equipment? In other words, we like to say, if it moves through the air, we can test it in a wind tunnel. The basic purpose of a wind tunnel is to find out how well an airplane flies through the air. What does that mean? First, we decide the purpose or the need of the airplane that will be provided. Let me explain. If the purpose is for armed conflict, a war, then you want a vehicle which will deliver its payload in the quickest time possible. But if your purpose is commercial, speed might not be your priority. You might be transporting the greatest number of passengers safely. The two vehicles that I just mentioned are at opposite ends of the research pole. A fighter jet is not concerned with the amount of fuel it uses, unless, of course, it has a long-distance mission. But the jet has to go fast. The commercial airliner, on the other hand, wants to save as much fuel as possible and get as many people on board to reduce the cost of tickets and increase the profits for the airline company. If the jets can get to the airport quicker, that's good too. NASA has a lot of different wind tunnels for different purposes. At NASA, we have over 42 wind tunnels that condition airflow in several ways to simulate speeds altitudes, and temperatures encountered by different aircraft. NASA has the largest wind tunnel in the world for testing ice formations on wings. Some test for takeoffs and landings, another test for jet noise, some test with lasers. The wind tunnel I work in can test the shapes of rotor blades, and one NASA site has the world's largest wind tunnel. This tunnel is so large a full-size airplane can be tested in it instead of a model. In the wind tunnel I work at, we test a wide range of aircraft under the speed of sound. And yes, we test rockets too. I mean, a rocket has to be launched from the ground into the air, into outer space, doesn't it? So next time you fly on an airplane, or if sometime in the future you get to fly on a rocket, just think of all the different kinds of research and all the different people at NASA who make it safe for you to fly.
Hi, I'm Monica Barnes, and I'm with the Strategic Relationships Office. I'm here with Roman Perez of the Ground Facilities and Testing Directorate's National Transonic Facility. And we're here to talk to you about some of the methods used at the nation's premier wind tunnel. Actually, the NTF is the nation's only large cryogenic wind tunnel. Roman, tell us a little bit more about the tunnel.
Thanks, Monica. I'm the manager of the National Transonic Facility. This facility was designed to recreate the actual flight conditions of aircraft, but using subscale models. We do this by changing the Reynolds number of this facility by either pressurizing it to 9 atmospheres or 130 psi, or by cooling the test gas down, and in this case we either use air or nitrogen, or by cooling it down to minus 250 degrees using liquid nitrogen.
Why would we use liquid nitrogen for the models?
Well, Monica, as a full-scale aircraft flying like a 747, 737, it's flying at full-scale Reynolds numbers, roughly 40 or 50 million. Very large number, but it's just a number. When we test the model in the tunnel, it sees much lower Reynolds numbers. So in order to test those full-scale Reynolds numbers to match the model, we have to shrink the size of the air down, or the test gas down to the model size. So to compensate for that, we use liquid nitrogen and we dump it into the tunnel by almost 2 tons per second. So it's a significant amount of nitrogen that goes into the tunnel, and that cools the tunnel, cools the gas, shrinks the gas down to the size of the model. That way it simulates, from the model's perspective, that we're testing a full-size aircraft in a tunnel that's only 8 foot by 8 foot in size.
Well, I think we have a way to show them how the gas shrinks, don't you?
Oh, yeah.
Let's show them. Here we have a balloon that is at full pressure atmosphere, and as you can see, it is a full-size balloon. It's blown up. What we can do is put it into the liquid nitrogen, and we can actually cool this down. The molecules in the air around the molecules is being cooled down and shrink it to another size. And as it re-enters the atmosphere, it can go back up to full-size molecules. So the air around it expands, and now these molecules are back to their full intent.
Well, to demonstrate exactly how cold this is, and again, the nitrogen is minus 320 degrees. We're using, it looks like clear liquid, and we're just using small crackers, and we're going to cool those down and see what happens. It actually boils off. So there's a big temperature difference between the liquid nitrogen and the air. It's roughly 400 degrees, from minus 320 to plus 70 degrees. And as they stabilize and the boiling stops, the crackers get down to the liquid nitrogen temperature. We'll pour off the excess liquid. Kind of a good way to clean the floor as well, as you can see the little bubbles of nitrogen going everywhere. And then we have very cold cryo crackers.
I think I'd like to try a cryo cracker as well.
Now these are very, very cold at the minus 300 degree mark, 320 degree mark, but since there's so little volume, so little mass in these crackers, they're cold, but they won't hurt you when you do this.
I like cryo crackers, don't you?
These are pretty good.
So there you have it. Now you've seen an example of how you shrink the gas down to the model size when we're doing our research.
Exactly. Hopefully you enjoyed the demo, and come and see us for a tour.
Thanks, Neutron. Okay, guys, let's do some wind tunnel testing of our own.
Cool.
So, how are you going to measure the wing efficiency?
Well, I guess we could try to measure the amount of lift the wing generates.
Yeah, that's a big part of efficiency on a wing.
What about drag, Dr. DeWitt?
Well, drag is another big part. I'm glad you thought of that. We should measure both. Why don't we start with drag? And then, what is drag anyway?
The amount of air friction?
Yeah, pretty much. It's what holds the wing back. You can see the effects of drag better on this computer model. Now, this is an airfoil, and these are streamlines of particles of air going past the airfoil. Now, you can see that there's a high pressure area here, that's in red, and there's a low pressure over here on the top of the wing, and that's what's lifting the wing up. So the low pressure is where the wing goes, and this is holding the wing back, so we have to overcome that with thrust. Let's investigate this further. We can use this computer program to model the changes that occur as air flows over the wing. And we can calculate drag. We can manipulate the airfoil and see how that changes the total pressure on the wing. Watch as I turn this airfoil 45 degrees. And watch what happens when I turn 90 degrees. So the cumulative pressure across the bottom of the wing has increased tremendously. And look how that has resulted in an increase in the calculated drag. We're up over 8 now, and up to 9 in some points, and we started out at 0.55. So these manipulations are very important for the testing of drag and lift on airfoils and their design. It's more efficient to test on computers first and then in the wind tunnel. Well, what is it about the wing that's affecting the drag?
The smoothness of the wing?
The shape.
That's right, Amar. Why do you say that?
I'm thinking of a parachute.
Like skydivers. When they're tucked in a ball, they fall faster than when their arms and legs are spread apart.
Well, can you demonstrate with these pieces of paper?
Well, sure, I guess. This one represents the tucked skydiver. This one represents the spread eagle. I'm going to drop them both at the same time.
Well, look at that. The crumpled paper representing the tucked skydiver hit the ground first, and the spread eagle skydiver hit the ground second. That's because the spread eagle skydiver, represented by this piece of paper, experienced more drag or air friction on its way down, and that slowed it down.
Oh, that makes sense. Well, we're ready to go, Dr. DeWitt.
Should I turn it on?
Sure. Let's get ready for our experiment first. We need to set up with the wing. We need to put on our safety glasses. Thank you. Eye protection is very important. And I believe we're ready to go. Okay, now that we're set up, let's test the drag on your wing model. Would you turn it on, please?
Yes, sir, Dr. DeWitt.
Okay, let's turn it up one more notch, and we'll see where the dial goes on our drag meter. Another notch. And another notch. Look at that. It moved to 2.4 on this scale, and our control was at 4 on this scale. So this means this is twice as efficient as our control.
That's pretty cool.
Excellent. You can turn it off now. Well, that was a great test, and we gathered valuable data about the efficiency of your wing. Wind tunnels are great in providing scientists and engineers opportunities to test their hypotheses and modify variables. Developing new plane designs, changing patterns and methods for air traffic, designing planes that are quieter and more environmentally friendly are all part of aeronautical testing the NASA way. Tune in next time for Future Flight, how computers are used in aerodynamic testing.